Most depictions of the solar system look like this, a rather straightforward model that describes the movement of the planets in a pretty simple manner. Most commonly referred to as the heliocentric model of the solar system, it often illustrates the motion of the entire system as just that of the planets around the stationary sun in fixed orbits. While it is a step up from geocentrism, heliocentrism is nevertheless still incorrect, because if you were really in this bird's eye frame, you'd actually see the sun wobble, as if it too were moving around something. As it turns out, everything in the solar system, including the sun, traces paths around what's referred to as the true center of the system. Known as the solar system's barycenter, its location and movement over time can be visualized using physics in conjunction with programming. The barycenter is what would be referred to as the solar system's common center of mass. The center of mass of a system is defined as the mass average position, that is, where the mass is located on average. For example, in the three-ball system, the center of mass would be the little orange dot that just appeared. The position of the center of mass of a system is always calculated relative to an origin, a point to which you attach a coordinate system. This point can even be the center of one of the balls. Doing this would give you the position of the center of mass with respect to the ball. The position of the center of mass is calculated just like how the average of something would be. First, you define a coordinate system with any point as the origin. Preferably, take a point that is located on one of the objects so that you get its position vector as a 0. Then, you draw position vectors to the points, or, if you're working with uniform objects, the geometric centers. Since we're dealing with a set of discrete objects, you can use the mass average formula to then calculate the position vector of the center of mass, like so. Of course, the mass distribution slash concentration of the system and the distance between the origin and the points affects how far the center of mass is located from the origin and where it is. For example, if I were to increase the mass of the blue ball, you would see that the center of mass essentially flips positions and switches to the heavier side or the more massive side of the system. On top of that, if I were to then increase the distance between the origin and the green ball, you would see that the center of mass then shifts a little bit towards the side of the green ball because of the substantial increase in distance. Applying the concept of the center of mass to gravitationally interacting celestial bodies yields you the barycenter. This two-body system has a barycenter located near the blue body, which is 10 times more massive than the red one. Since the total momentum of the system is zero, the barycenter stays put and doesn't move. However, this may not be the case all the time, as is made evident by taking a look at this three-body system. Since the total momentum, that is the barycenter's momentum, is non-zero but also constant, it moves in a straight line. You could also say that the constantly changing positions of the bodies are capable of changing the position of the barycenter. Keeping all of this in mind, we can say two things for sure. Because of the sun's gargantuan mass in comparison to everything else in the solar system, the barycenter is going to be located pretty close to it. And since the planets are constantly changing positions, the barycenter will too. With these things out of the way, we can finally start calculating the position of the barycenter. For the basic setup, we're going to be needing some things. The first of which is going to be the knowledge that the solar system is a set of discrete objects and will require the mass average formula when it comes to calculating the position of the barycenter. The second is a technical tool that's going to help us a lot. It's called SPICE, and it's provided and maintained by NASA. SPICE is a pretty good tool, but more specifically, we're going to be using SpicyPy, which is a Pythonic wrapper for SPICE. SpicyPy can be used to generate stuff like position vectors and sky coordinates. The last few things we're going to need are some assumptions about our initial model. The first of which is going to be a heliocentric coordinate system. This means that the sun is going to stay at rest and not move. This also means that its geometric center is going to act as our origin. The next assumption would be that the sun's gravitational pull on the planets is the only force considered, so the planet's own gravitational interactions are not going to matter. We're not going to include them. along with the equal and opposite poles exerted by the planets on the sun. Since the sun won't be moving, you can just ignore them. The only forces that will matter here are the ones exerted by the sun on the planets, and each planet is going to have acting on it just that pole as its net force. Next, the final assumption is that we know the initial position and velocity vectors of each planet. So, when we're starting our calculation, we know exactly where each planet is located with respect to the sun and also where it's initially moving. With these assumptions, the basic setup is now complete and I can actually move on to the method. At time t equals to 0 or the initial date, I know that for a planet, its initial position and velocity vectors are known, along with the fact that the net force acting on it is equal to the gravitational pull of the sun. Using Newton's second law and universal law of gravitation, I end up with this equation for the acceleration vector. Now, the initial velocity vector plus the change in velocity vector would be equal to the new velocity vector, which we can use to similarly update the position vector. The head of the new position vector gives us the new position of the planet, which we can now update. The method then repeats itself for the next time step dt seconds, and instead of using r0 and v0, it uses the previously calculated r dash and v dash as the new initial position and velocity vectors. Everything else remains the same, just with new variables. Using this method at t is equal to dt gives us the new position of the planet. Repeating this method until we reach the final time date gives us the position of the planet at every single time in between. Of course, we're not going to do this for just some arbitrary planet. We're going to do this for all 8 planets in the solar system, and using their positions at different instances of time, calculate the position of the Barycenter using the mass average formula. This is going to be with respect to the sun. And just to compare how far off we were with our prediction, I'm going to compare it with the observed value. The first block of code is going to have the modules we're going to use. So I decided to import SpicyPy as Spy, NumPy as MP, Matplotlib so I could actually plot stuff as PLT. Though I didn't use it, I decided to import pandas as PD and datetime as DT. Next, I decided to import some kernels using SpicyPy's French function, one for ephemeris time, another for physical parameters, a third for gravitational parameters, and for the state vectors, I went with this kernel. This would have been it, but unfortunately, the state vector kernel didn't have the position of the planets, only their barycenters beyond Mars, so I decided to import those individually. With the help of the datetime library, I can now define my initial date, final date, and time interval. For the initial date, I decided to go with January 1st, 2025, right at midnight. Next, I converted this date to ephemeris time using SpicyPy, and then defined delta t, which was the time difference between the final date and the initial date. After adding said time difference to init, I got fin, which in this case was 1 year ahead of the init variable. I also decided to convert it to ephemeris time and then print out the values to see if the program was working or not. Next, I decided to define the time interval, which would be a lin space that started at the initial ephemeris time, ended at the final one, and had 365 steps in between. This meant that I had ephemeris equivalents for every single day of the year, which when printed out looked legit, but just to double check, I decided to reconvert these values to their datetime equivalents, and what I noticed was, when I printed them out, they all seemed to give me successive days of the year at successive indices, which meant that the program was working. Spice has its own way of identifying bodies, using integer codes. This is why I decided to build a dictionary with the appropriately named bodies as the keys and the IDs as the values. Spice gives the Sun an ID of 10, whilst the planets get 3-digit codes that all have the format X99, where x ranges from 1 to 8. Since I couldn't directly retrieve the mass of the body from space, I decided to create a for loop that extracts the gravitational parameter, or mu as it's often called, of every ID in the solar system dictionary. Using the mu of the body in place of the mass in the mass average formula doesn't make any difference, since the big G's would factor out from the top and bottom and cancel, giving us the original formula. Seeing as how important the mu of the sun was to our calculation when it comes to acceleration and stuff, I also decided to make it a new variable. For the observed path of the Barycenter, I created an empty list that has a new three-value array that represents the position vector of the Barycenter added to it every time the for loop that I'm creating goes through a value, an ephemeris value, in time int. To get these position vectors, I decided to use the spkgps function, which takes as its parameters what we're observing, the ephemeris time, the reference frame, and the observer. For the reference frame, I decided to go with Eclipse A2000, which means that this was being done in the frame of the ecliptic plane. Recalling that the barycenter is going to stay pretty close to the sun, I decided to convert these values to solar radii using the BODVC function, from which I extracted the radius of the sun. Doing so gave me values that seemed to stray no farther than 2 solar radii in all three directions. Using matplotlib, I can now plot the observed path that we got on a subplot. Center at the origin of the subplot will be a circle that is supposed to represent the sun, as if it were being viewed from the top or bottom. I decided to go with the radius of 1 because I wanted the scales to be in solar radii, which is what I did just before plotting the actual position observed array. And this is the result I got. 1 year's worth of movement from 2025 to 2026. On a scale of something as grand as the Barycenter's movement, 365 days is pretty small, so I decided to bump up the number to 1400 days and noticed that the Barycenter seemed to be curving inwards. Increasing that number to 5000 gives me a full loop, which really shows the complex path that it follows around the sun. Next, for the theoretical part, I decided to create a bunch of lists that would hold the predicted positions of the planets, so that I could later use them to calculate the expected position of the barycenter. For the code that was going to calculate the theoretical path of the barycenter, I decided to go with a for loop that would first calculate the initial position and velocity vectors of every planet in the solar system with respect to the sun. This meant that I would be leaving the first value of the solar system dictionary out, 10, which would be the sun's very own SPICE ID. When printed out, I got the x, y, and z coordinates in kilometers and velocities in kilometers per second. Inside the initial for loop, I decided to implement another one that would make use of the computation method that I introduced at the start, the technical term for which is the Euler method. When it comes to long and tedious calculations like this one, the Euler method is a reliable technique that gives a pretty good estimation of the real deal. After defining the acceleration, computing dt, and then updating the velocity and position vectors for every dt we get until we reach the final date, I appended our node to the empty list that I created based on the ID of the body that it was computed for. I did this for all 8 planets, after which I converted all these lists to arrays so that I could directly use them to calculate one that has the predicted positions of the barycenter at all times in time int. With everything pretty much done, all that was left was for me to implement the mass average formula to calculate the theoretical position of the barycenter. I did this by taking the position areas of the planets, multiplying by their respective mu values, adding all of those products up, and then dividing by the total sum of all the mu values that I had, which includes the sun's. Of course, since all the positions of the planets were in kilometers, so will be the barycenter's position with respect to the sun. But since my subplot had axes that scaled in solar radii, I had to convert all these predicted positions of the barycenter that I had to solar radii by dividing by the radius of the sun in kilometers, which I again extracted using spider.bcd. Printing the values out, I expected the gap between the theoretical and observed values to be rather small. Fortunately, it did turn out to be that way. I couldn't see any significant differences between the theoretical and observed positions. Given that the values matched, I expected the paths to follow suit and do so too, plotting the theoretical movement of the barycenter on the same subplot as what has been observed gave me the following result. An almost perfect overlap. Both paths seem to superimpose on one another really well. After seeing this initial plot, I decided to play around with the code a little bit. First, I plotted only the theoretical path of the Barycenter and then added the observed path in later just to see if I could make out any visual differences, which I couldn't. Next, I moved on to the values of delta t, the time difference between date initial and date final. I wanted to see just how long it would take for the predicted path to deviate ever so slightly from what was observed. The answer turns out to be pretty long. It took me around 10,000 days to finally notice slight deviations. Sometimes the theoretical path seems to curve inwards, and other times outwards. This level of accuracy just goes to show how good of an estimation the model that was full of assumptions turned out to be. Looking at the paths themselves, you infer something that could go either way. In spite of the sun's ginormous mass, the solar system's scale, its distances, are large enough to pull the barycenter out of it. Or, in spite of the large scale of the solar system, the sun is massive enough to keep the barycenter pretty close to it. Just to see how far off I was from the observed path, I decided to calculate the percentage error. I did this by defining an error variable that was just the difference between the theoretical and observed value divided by the observed value as a percentage. Printing it out, you can see that the percentage error starts off at about 0.1% and then rises to around 2.5. Overall, this indicates a pretty accurate model, but the reasons as to which I think it rises are the gravitational forces that weren't considered and the size of dt. dt is still about a day's worth in seconds long. Maybe if it were smaller, the model would be more accurate. Pairing that with a program that accounts for the gravitational perturbations of the planets and the sun's movement would make it even more accurate. Additionally, you could make an animation using something like WebVPython. This one here shows the entire solar system, and when you zoom in, you can see that the barycenter moves exactly like what we saw in the plot. This WebVPython approach differs from the VSC one in its absence of libraries and plots, so there is no SpicyPy or Matplotlib here. We're still using the other method though, and we still have the same initial conditions. We're just applying them on a canvas. Of course, this is still heliocentric. To get the barycentric system, we're going to have to switch the reference frames to the barycenter. And what we observe is, it now looks like the Sun is the one orbiting the barycenter. This is the reference frame that we use when it comes to calculations nowadays. And the ICRF, which is internationally recognized as the best inertial reference frame that we have right now, also uses the barycenter as its origin. The wobble of a star against the backdrop of the night sky can also indicate the presence of an external barycenter, and therefore exoplanets that are pulling on it to cause that wobble. If you're looking for more space science and programming content, I recommend Dr. Thomas Albert's channel. There, he has quite a lot of playlists that each deal with a different aspect of space science. In his general Space Science with Python playlist, you'll even find a video on the Solar System Barycenter. You can use it to learn how to actually plot stuff using Matplotlib and SpicyPy. In the description of this video, you'll find both the WebVPython project link and the GitHub repository for the Jupyter notebook we used. If you have any suggestions or questions, mail them to me or drop them in the comments.